in this last segment in today's lecture, we will analyze the mincut algorithm proposed by Karger. And just to recollect, this is the lemma that we are going to prove. With probability at least 1 over n choose 2, the sets S and V minus S, these are the sets that come out as an outcome of Karger's algorithm. These two sets, this partition induces the smallest cut. And this is the claim that we want to prove. And to prove that, we will focus on one of the minimum cardinality cut sets. There could be many minimum cardinality cut sets. What we are going to do is pick one of them. So, C star we call it, and we will prove something slightly stronger than it is required. We will prove that the probability of the cut produced by the algorithm, this S and V minus S, is actually corresponding to the cut set C star. That probability is itself greater than 1 over n choose 2. Now, if there are other cut sets, naturally the probability with which the algorithm will find one such minimum cut set is only going to be increased. So, we are therefore being conservative in our claim here. So, now let's go proceed with proving this claim. And towards that, let's look at the execution of Karger's mincut algorithm. And in each step, one of the edges was picked and contracted. So, let's call these edges E1, E2 and so on up to En minus 2. Of course, we only would contract n minus 2 edges, because at that time we would be left with just 2 vertices, and therefore we would stop. What is the probability that the algorithm succeeds? Well, if all of these edges that were picked for contraction missed C star, then what we will be left with at the end is going to be C star. Another way of stating this is, as the algorithm progresses, if we pick an edge and it happens to be an edge in this cut set C star, then the algorithm is going to fail. However, if all the edges that we pick as the algorithm progresses are outside of the set C star, the cut set C star, then after the n minus 2 edge contractions take place, what we will be left with is exactly the edge set C star. Of course, if that were not the case, meaning if we if E1 through En minus 2 did not were not part of C star, but then if you were left with something other than C star, then C star cannot be the minimum cut. So, so this is going to be the criterion for success of our algorithm. So, none of the edges that we picked are in the element in the set in the cut set C star. Let us say the cardinality of C star is some k. Clearly, the minimum degree of G must be at least k. Why? Because if the minimum degree was something less than k, then you have a smaller cut. So, for example, if k is 5, but if one of the edges has degree just 3, well, that is a contradiction, because you have a cut of just size 3. So, the minimum degree of G must be at least k. and this continues to hold as an invariant for all intermediate multigraphs that are produced, because at any point in time, if the degree goes below k, then we have a cut set that is corresponding to the original graph, that a cut set with in this that can be obtained in this manner. So the degree, the vertex with the supernode with degree less than k can be put on one side, and all other vertices on the other side, and the cut set that induces will be of cardinality less than k, and that will contradict the assumption that we have that k is equal to the cardinality of a minimum cut set. So now let's one more notation. Let G sub j denote the graph after j contractions, and here you notice that Gj has n minus j vertices. Well, G0 will have all the n vertices. G1 will have, after one contraction, will have just n minus 1 vertices, and so on. And the number of edges, you have to recall two things. Gj has n minus j vertices, and it is of degree at least k, a minimum degree at least k. So the total number of edges, therefore, must be at least n minus j times k divided by 2. Now the degree has to be shared. So each edge contributes 2 to the degree. So if you look at the to the total degree is n minus j times k. So the number of edges will have to be at least n minus j times k divided by 2. Okay. What does that mean? What does this mean? Now we can start, and this is true for all j. This is true for all Gj. Okay. So with that, now we have the mathematics needed to continue with the proof, and what we want to do is bound this probability that the cut produced by the algorithm is in fact the specific cut C star. Okay. So what is that? That this event is the probability that the first edge, in fact this is nothing but the probability that none of the edges that were chosen by the algorithm intersected with C star. Okay, so let's write that out more carefully. That's the probability that E1 does not belong to C star times, now you're going from j equal to 1 to n minus 3. So the probability that E2 does not belong to C star, probability that E3 does not belong to C star, and so on up to probability that En minus 2 does not belong to C star. But each one of these subsequent probabilities, notice, require that the previous edges also do not belong to C star, because if any of the previous elements edges belong to C star, then the algorithm is already not going to lead us to C star. So just working through that product, we get this. What we have here is the probabilities that each of the Ej plus 1s don't belong to C star. Now, what is the probability of actually picking an element from C star? Well, that probability is going to be at least k, because k divided by the total number of edges. K is the cardinality of C star. So that the bad event would be that we pick an element in C star. So that's so this is the probability of the bad event, which would be that we pick an element from an edge from C star. So, there are k edges in C star. The total number of edges, and this is for a particular g j, the total number of edges we have already seen is this quantity. This is the probability of the bad event. Now, we are considering the good event, and therefore, 1 minus of that. So, why what is the good event? Good event is that the edge that we picked is not actually an element of C star, and this is the good event for one particular g j, and this such a good event has to be occurring for every j, and therefore, we take a product over all j values, and this is the expression we get. Now, solving this expression, each one of these, it's easy to see, is going to be of the form n minus 2 by n, n minus 3 by n times, and so on, up to 2 by 4 times 1 by 3, and so on. Of course, there's going to be a lot of cancellations. We'll be left with so all these terms up to 2 will get cancelled, and all these terms up to 3 will get cancelled. So, there will be an n minus 2 over here. Starting from that, you will have cancellations. So, we are left with 2 over n times n minus 1, which is nothing but 1 over n choose 2 as we required. And so, this completes the proof of our lemma. What we are left with is that we need to boost the probability of success. 1 over n choose 2 is too small a probability of success, but it is not very difficult to boost this probability. We simply have to repeat the algorithm, say some c log n times n choose 2 number of times this quantity. So, we have to repeat it that many times. So, now the probability that all of these repetitions will fail is going to be 1 minus 1 over n choose 2, the whole raised to c times n choose 2 times log base e of n. So, here I am using log base e, and this ends up being at most 1 over n to the c, which is what we need for high probability. So, this gives us a guarantee with very high probability that the algorithm will indeed find, in particular, the cut set C star. We are finally left with running time analysis. This particular algorithm is a Monte Carlo algorithm. So, the running time is actually a deterministic quantity. Of course, the algorithm may fail to produce the correct min cut, but with a very small probability. So, a quick exercise here, you have to show that each run of the Karger's algorithm takes O of n squared time. You have to be a bit careful about this, but it is not hard at all. And if each execution takes order n squared time, and we are going to repeat this something like c n choose 2 times log n times. Therefore, the total running time ends up being O of n to the 4 times log n. So, this is the running time. There is some techniques to improve the running time, but for our purposes, this is it's still a good polynomial time running time, and moreover, the algorithm is very elegant and simple and easy to implement. So, thank you very much.